So in the previous lecture, we talked about what is maximum likelihood estimation and the problem of zero probability. So if an n-gram is not found in the training data, it is assigned zero probability, but in real situation, the probability is not zero. The probability is zero only in the training data. If the trigram is not present in the training data, that doesn't mean that it is not present in the language. So we need two tasks there. One is the n-grams which are not present in the training data, they should be assigned. Though they are not in the training data, we should not bluntly give zero probability, because there is a possibility of that n-gram existence in the language. Secondly, the training data may have more frequency of particular trigrams or n-grams. Those have to be discounted because they are more number of times in training data. That doesn't guarantee that the same thing will happen in the language. So we need two things. One is adding minimal probability to the n-grams which are not seen in the training data. Secondly, the n-grams which are more frequent in the training data should be penalized or should be normalized with a discounting factor. So this technique where we avoid zero probability in maximum likelihood estimation is known as smoothing. So we'll see two different smoothing techniques in this class. The first one is known as Backoff smoothing. So Backoff smoothing, it is a simple technique. For example, you are dealing with trigram. Trigram, that means he is playing. That is not seen. So he is playing has zero probability. So the Backoff smoothing tells, because trigram is not seen, let us fall back to bigram. Let us assign the probability of he is having, he is probably assign bigram's probability. If the bigram is also not there, assign unigram probability. So this is known as Backoff smoothing. Suppose an n-gram is not seen in the training data, assign n minus 1th probability. That is known as Backoff, falling back. So the Backoff probability, suppose it is trigram. You are trying to find wi minus 1, wi minus 2. If that probability is greater than some threshold tau, then you use a discounting factor. This is a discounting factor because it is greater than the threshold. If it is less than a particular threshold, then use lower order n-gram. So you use the probability of wi and wi minus 1 rather than wi given wi minus 1 and wi minus 2 multiplied by alpha to ensure that sum of all the probabilities is equal to 1. So it is not, don't be much perplexed about the equation. It is simple. If the frequency is high, multiply it with a discount factor less than 1. If it is less, then if it is trigram, use the digram probability. If it is digram, use the bigram, use the unigram probability multiplied by a rationalizing factor alpha to ensure that the sum of the probabilities is equal to 1. Let us see some example. He is smart. What is this? Trigram. Trigram. He is smart. And the count is 1. And the threshold is 2. Because it is less than the threshold, whether it is 1 or 0, what we do? Instead of considering smart he is, we will fall back to the probability of bigram smart is, and we multiply that with alpha, which is a rationalizing factor, to make the probabilities 1. So this is our alpha, which is calculated ensuring that all the probabilities are equal to 1. Because when we discount some probabilities, we should follow the rule that all the probabilities should be equal to 1. Then this is the first model of smoothing, Backoff smoothing. What is smoothing? If trigram doesn't exist, fall back to bigram probability. If probability of bigram is not in the training data, fall back to unigram. Instead of that, we can use another method of smoothing known as linear interpolation. That means take unigram probability multiplied by a factor lambda 1, take bigram probability multiplied by factor lambda 2, take trigram probability multiplied by lambda 3, linear interpolation. Even if this is 0, still you have non-zero probability here. It is something like summarizing the thing, and lambda 1, lambda 2, lambda 3 should be equal to 1. So to calculate that, the probability is sigma of lambda j into the probability of trigram, then lambda into probability of bigram, probability of unigram. And to calculate lambda, we can use expectation maximization algorithm, and from that you can, that lambda is the factor that returns the maximum performance. So, or otherwise you can say that lambda value is the value at which the given model perplexity is very, very low. In the last classes we have seen that lower the perplexity, higher the performance. So why do we need smoothing? Because in maximum likelihood estimation, we'll be calculating the frequency of given n-gram by the total frequency. But if that is 0, we need smoothing. In the smoothing, we have two techniques: Backoff technique and linear interpolation technique. These are known as lower order models. But the problem with falling back or linear interpolation is they favor certain frequent words. Suppose in English language, the most frequent words are the, of, and. These are found more and more. So if you fall back, they will have more probability. So we need to capture whether the given word, not only our modeling should not depend not only on the number of occurrences. So for example, the, of, and, they occur more and more. That means they are not the real valued, but we want to capture not only the count, but how many different contexts they may appear. For example, San Francisco is a city name. So Francisco appears often after San. Generally, by single, Francisco doesn't appear. So it may appear in different contexts. So maximum likelihood assigns higher unigram probability to Francisco because it is occurring along with San, but alone it is not a general purpose word. Because it is coming with San Francisco, it is assigning more. It is not here. The thing is, we should not depend only on the count, but we should also see the context. Francisco is occurring, but in what context? When the San is there. If there is no San, there is no Francisco. So we should assign the probability to the Francisco not only on the count, but also on the context with which it is occurring. So this type of smoothing is known as Kneser-nay smoothing. So the earlier models, lower order models, what are they? Backoff smoothing, and another one is linear interpolation. They depend only on the count, but this method depends on the context diversity. How many different contexts a given word appears. So here we calculate the probability of continuation of Wi, number of bigram context ending with Wi by total number of bigram types. So we are not depending only on the count or frequency, but we are depending on the context. Totally, how many bigram types are there? That is the denominator, and in the numerator, number of bigram text ending with Wi. That is the context diversity. So in Kneser-nay bigram, the formula for smoothing is the probability of a bigram given Wi minus 1. Wi is calculated as maximum of frequency of the bigram minus d, where d is the discounting factor. We already told that if a bigram or trigram occurs more and more frequently, we need a discounting factor, or 0. If it is 0, we'll consider this one, the maximum, by the frequency of the unigram into lambda. Lambda is the factor which is multiplied with the probability of continuation, the context in which it is calculated. So here we'll be seeing this in detail. So the first term, this term, is the maximum likelihood, the count. If you remember where we calculated the maximum likelihood, how did we calculate the maximum likelihood? This is one. The count of trigram by total count of the bigrams. So the same thing here, but with the discount factor. Then the second term, lambda Wi minus 1 into p continuation, it is the discounted mass. So we are calculating the probability not only on the frequency, but also on the context variety. How many different contexts it occurs. So here there was a simple modification to this Kneser-nay smoothing based on how many times it was occurring, how many times it is occurring. So the discount factor will be calculated based on the number of occurrences D1, D2 and D3 plus, for example, San Francisco occurs 20 times, San occurs 20, and discounting factor is 0.75. And Francisco occurs only in one context after San. If there is no San, there is no Francisco. So we calculate the probability of that given San occurrence of Francisco is 20 minus d, the count minus d by the count, total count, in plus lambda into p continuation. That means We are penalizing Francisco because lower context diverse. It is occurring only with San. So this method is a very effective method, and this modified version, calculation of discounting factor, is very interesting. For example, you have n-gram, it is occurring only once. Number of n-grams occurring only once are n1, number of n-grams occurring twice are n2, and then we calculate the estimate, the tendency of n-grams to repeat as n1 by n1 plus 2 n2. What is n1? Number of n-grams occurring exactly once, number of n-grams occurring exactly twice. Then the discount factor, when for singletons only once, it is calculated as 1 minus 2y into n2 by n1. So this n2 by n1 helps to scale the discount depending on how many 2 count n-grams. N2 is occurring twice are there. Similarly, D2, 2 minus 3y n3 by n2. D3, 3 minus 4 by n4 by n3. These are the different discount factors for D that is used in here. This is modified Kneser-nay smoothing. So Kneser-nay method provides generalization for unseen rare word sequences. Remember that Backoff smoothing and linear interpolation, they only count the number of times it is occurring. But Kneser-nay smoothing also counts the context, how many times, how many different contexts the given word appears.